All right, so continuing on in the notes, we just graphed this one here, which was a degenerate conic with two intersecting lines. So we'll see what this one is. I have a sneaking suspicion this might be a degenerate conic as well. So I can't tell by looking at it. In fact, if I were to guess what this is, I'd guess a circle, because these are same sign coefficients and they're both the same. So I would say it's probably going to be a circle. Let's see. X squared minus 4x, leave a space. Y squared plus 2y. Let's move that 5 over. Complete the square. Half of 4 is 2, squared is 4, add 4, add 4. Got to balance it out on both sides. Half of 2 is 1, squared is 1, add 1, add 1. So this factors into x minus 2 squared plus y plus 1 squared equals. And again, this goes down to 0, and that's whenever some weird things tend to happen. So this one, we just need to kind of think about this a little bit. I want to add two numbers, and because these are even coefficients, I want to say these are both going to be positive. When you square a number, you always get a positive, right? A positive plus a positive is a positive. So you might think that this is an impossibility because two positive numbers can't add up to 0, but when you square a number, you don't always get a positive. If this number is 0, when you square it, you'd get 0. And if this number inside was a 0 and you squared it, you get 0. You could get one solution. The solution would be when this is equal to 0 and when this is equal to 0. So what do we call all the points where x is equal to 2 and y is equal to -1? Well, it's just that point, 2, -1. So if you recall, 2, -1 is one of those degenerate conics. It's a point. It's where you have the double nap cone and you cut the plane. The plane kind of cuts through here, kind of like right there at that point. I can't draw three-dimensional shapes. So we just have a point solution. When does that happen? If you have a plus in between your squares equal to 0. When does two intersecting lines happen? If you get 0 on this side and you got two squares with a minus sign in between them. The only degenerate conic we haven't talked about yet was the straight line degenerate conic. Explain why the following conic is the empty set. Well, here you're squaring something plus you're squaring something, and this is somehow supposed to be equal to a negative. The smallest two squares could be added together is 0. It is impossible to add two squares and get a negative if you're in the real coordinate plane. So if we're in the real coordinate plane, this is impossible. So no solution. Sorry, I'm not really explaining it, or I explained it, but I didn't write it down. My bad. So this is general form of a conic, and we did talk about this in class. And we tried to give you an illustration to tell you what the A does, what the C does, what the D and E do, what the F does, and then what this B term does. You kind of should know those things a little bit. Use computer software to explore. I think I did that in class already, so I'm not going to do that. I think I've already done that. Comments and observations. Here we go. Because the effective parameters B and F of the effective parameters B and F have on the conic, B and F, it is difficult to predict the type of conic when it's in general form. Some combinations of these parameters will create no graph. We illustrated that up here with this example here. There was no graph on that one. So general form equation isn't always going to be a conic. It could be an empty set and have no graph at all. Or it could be a degenerate, or it could be your standard circle, ellipse, hyperbola, and parabola. You are not responsible for graphing rotated, of course. I do want to point out, though, that this is one of our base graphs. If you remember that base graph, that was actually a hyperbola. We never really looked at it as hyperbola, but it was. The following theorems can help us identify the type of conic from the general form equation. You are responsible for the first, and you are not responsible for the second. That is very true. We're talking about a testing situation. So this I expect you to know, and it's kind of common sense. This you do not need to know, and it is certainly not common sense. In fact, I think it's kind of surprising. And to be honest, I've never really seen a proof, or really, I don't even really know why this is true, but so I can't really explain it to you. I'm sure you can find it if you wanted to dig a little bit. So given that a conic is a circle, ellipse, hyperbola, or parabola, and the general form of the conic, and it has no xy term, you can determine the conic as follows. So the idea here is you need to know it's not degenerate. If you know it's not degenerate and it's one of those four, and there's no x squared term, you can decide what the graph is going to be by looking at this stuff here. If a is equal to c, that's these two numbers in front of your x squared and your y squared. If those are equal to each other, you know it's a circle. If a and c have the same sign but they're not equal, then it's going to be an ellipse. If a and c do not have the same sign, then it's a hyperbola. I think all of these are kind of under the assumption that a and c are not 0. So they can't both be 0. If they're both 0, then it kind of throws everything off. And then the last one is if a does not equal 0 and c does, or if a equals 0 and c doesn't, then it's a parabola. Basically, if there is no x squared term, then you just have a y equals x squared parabola. If there's no x squared and there's only a y squared, then you have a parabola. So this allows you to very quickly and easily determine which graph is which, as long as you have these criteria met, right? Here's an interesting theorem. Given any conic, given a conic is a circle, ellipse, hyperbola, or parabola, you can determine the type as follows. And this is kind of interesting because basically this is that discriminant whenever we had a quadratic, but this is really different. I mean, this isn't a quadratic at all. This is the a squared coefficient, the xy coefficient, and the c coefficient, the y squared coefficient. But surprisingly, it kind of looks exactly like the inside of that quadratic formula. So if this quantity is greater than 0, it's a hyperbola. If this quantity is equal to 0, it's a parabola. And if this quantity is less than 0, it's an ellipse. You are not responsible for this. I kind of just put it in as a FYI, hey, look at this weird connection to something that feels like it's, I don't know, for me it's surprising. Okay? All right. Examples. So these are test questions types of examples. Without completing the square, just look at them and decide what they are. All right, so I got an x squared and a y squared. They have different signs, so it's a hyperbola. I got an x squared and a y squared. They have different signs, so it's a hyperbola. You might say, well, they're the same. Well, it doesn't matter if they're the same if they have opposite signs. So here we have show you my grades, that'd be bad. Here we got an x squared and a y squared. They're both positive, so that means it's an ellipse or a circle. They have different numbers, so it's an ellipse. Got a y squared but no x squared, parabola. Got an x squared and a y squared. Now you might say, well, they got opposite signs. Look, they're on, but we got to get it on the same side. Really doesn't matter about the rest, right? So they're both the same sign and they're both the same number, so that would be a circle. Not testable examples. Okay, so this one here, so this is my A, this is my B, C, D, E, F. All right, but the only thing we really care about here is B squared minus 4AC. So let's calculate B squared minus 4AC. My calculator on? I need my calculator in a little bit, so let's fire it up. So this is equal to 6 squared minus 4 times A times C. That is 36 minus 12. That is 24. And that is definitely greater than 0. So according to this little theorem here that I really didn't prove or justify in any way, shape, or form, if it's greater than 0, it should be a hyperbola. So according to that, it's a hyperbola. Now, we didn't learn how to graph these by hand in class. We didn't really learn how to handle that xy term. I think in advanced pre-calc you'll do a little bit of that. But I can show you, with the calculator at least, kind of verify that the theorem is true. And that it works for in this one case at least, because I'm not proving it for everything. So let's remember this. 3, 6, 1, 3, negative 1, negative 1. There's no way I remember all that. So if we go to a graphing page, now we didn't do this a whole lot, or we didn't do it at all. If you go to menu, instead of graphing a function, if I graph a function, I'd have to solve that thing for y. That'd be a lot of work. If you go to equation templates, you go to conic, you can put in the general form of a conic. 3, 6, 1. That's not even right. 3, 6, 1. Okay, I got it right so far. 3, negative 1, negative 1. 3, negative 1, negative 1. And that is a hyperbola. It's a hyperbola where the two vertices are very close to each other. In fact, you can even kind of imagine if those vertices get even closer to each other, it would make the two intersecting lines, but that's definitely a hyperbola. So it works. It's rotated. It's a rotated hyperbola because it has an xy term. Okay? For your partner test, this is stuff you need to know. Good luck getting ready for it. Do that worksheet. Do the practice test. There's some good problems, good test-like problems on those documents. All right, good luck.